Yes.
So today, as Theo said, I would like to talk about fermions, not bosons. So today, my goal is to let you understand the title of my talk. So I will go to derivate thing, of the Vlasov equation, which I will introduce soon for the people who are not used to. And then I will gonna talk about what is fermionic manybody Schrödinger system is. And then later I will introduce what the Husimi measure is, and I would like to talk about how to prove, but I expect to lose almost all the audience when I'm talking about the proof. So, okay, let's go. So, as I said, so I will gonna talk about what the Vlasov equation is, and what the fermionic manybody system is, and Husimi measure, and so how. So I'm gonna try my best to bring you until the Husimi measure. So first, Vlasov equation. So the Vlasov equation is describing plasma. And what is plasma? Like this lightning, amazing picture taken by me from Città di Bagnoregio. I was lucky to take this picture. So yeah, so plasma is ions, like it's called a fourth state of particles, or yeah, and which are ionized particles. And then if we have a lot of ionized particles and the motion of them is not really following Newtonian, it is following Newtonian physics, but somehow the electromagnetic force is sort of governing the system, so that the behavior of the system is different. Amazing, right? So plasma is actually everywhere, other than this kind of nice lightning situation. So for example, like nowadays we cannot really see the neon signs anymore, but so the neon signs, inside the neon signs, they are full of plasma particles. And for example, also like at least in Korea, any like glass shops are having this kind of plasma ball. I don't know if it's the case in Italy, but yeah, that kind of amazing toy is filled with plasma. And sometimes in Norway or in Canada, one can see aurora, right? Like beautiful sky. And that's consists of plasma. So plasmas are everywhere. And understanding the nature of plasma is important. Okay, so how to understand this? So understanding means given initial data, we want to know the dynamics of the system. So how to so Vlasov was interested in such kind of system.
What's the problem online?
Mm-hmm. I think it should be like before, and he should pin that.
No, just connect to someone.
Okay, so let's talk about Vlasov equation again. So Vlasov in 1930s, he wanted to talk about plasma, and he derived somehow Vlasov equation, which is describing the motion of plasma by using this idea. So he, as a physicist, he thought that plasma consists of particles, continuum. So it's not really particles, but he thought about plasma as a continuum in phase space, which means in spatial variable q here in this case, and momentum variable p. And then he was thinking that, okay, if there is a plasma, if it is a reasonable thing, it should move in the phase space continuously, which means it doesn't teleport and it doesn't gain energy out of nowhere, or any plasma particles or plasma is created at any point or annihilated anywhere, so anywhere at any time. So it should be quite smooth. And using that logic, he said that okay, density of the plasma at A is moving along the time, and it should move to maybe B and continuously, so that the area of it should be conserved, or like it should move continuously. Yeah, in the phase space. And then this phenomenon can be described in the PDE sense, saying that okay, so at any point in the phase space, at any time, the change of the density of the plasma at that point should be attained by just watching the plasma flow through along the boundary. So if the plasma is leaking from the area A, the density should decrease, and if it is getting plasma, getting inflow, the density of the plasma at that point should increase. That's the logic. And then so this term is about the change at that point, and this term is the divergence in phase space. So it captures the inflow and outflow of the plasma at that to the point or from the point. So this is called continuous equation, and we can expand this equation. So this was divergence in phase space P and P variable and Q variable, so that you can really expand it, the divergence, into Q variable divergence and P variable divergence, which are three-dimensional. And then because this is partial derivative, you can think about the change of variable. Chain rule. We can think of a chain rule, and then up to the first line, it's easy, nothing. And then the second line is again nothing. And so we have four terms, and these four terms, two of them can be ignored, because if we assume that the position of the particle should not related to the velocity or momentum of the particle at that point. So they should not talk to each other. So Q variable derivative of P should be zero. And then the P dot is there. P dot means the force, because you know F equals ma, and ma is a P dot, right? Because ma is mv dot and mv is P. So P dot is a momentum change, which is a force. And here, as I said, plasma is feeling electromagnetic force. So this is the electromagnetic force from Maxwell's equation. And because we can think, okay, if we are in the classical regime in some sense for general relativity people, so that c, the speed of light is infinity. We think of that kind of situation. Or if there's no really magnetic field effect, we can ignore this P dot, right? Because we drop this term which is related to P, and then because E is nothing to do with P, so P dot there, divergence in P for P dot is zero. So we drop two terms. Now we don't have this term, and we don't have this term. So now we only have those two terms, and we write them here. So here, this one, and we have this one, and here we have this one, which is this one. So because, as I said, P dot is E, and this is called Vlasov equation because this E is specially chosen to be the electric field generated by itself. So if this means Vlasov was derived his equation assuming the speed of light is infinity and electric field that it feels is generated by itself. And then this is describing the motion of plasma. And this is what I wanted to talk about. Vlasov equation. And there are many results in this direction, but yeah, I will stop here for the moment. And yeah, so as a mathematicians, we can talk about the well-posedness, uniqueness, many things, and about this direction. Okay, good. Okay. So to me, the question was, okay, Vlasov derived his equation using Newtonian mechanics, classical Newtonian mechanics, and it works well, pretty well. And people are using this to predict many things, and it works well. But the problem is, to me, the problem is actually Vlasov equation. Usually, people are using this to describe many electron systems, like a lot of them. But as far as I know, as far as I was educated, electrons are quantum particles, like this. So if one shoots electron through the double slit, we don't see. So if electrons are classical particles, we should see the two stripes in the tuning. But if we shoot electrons through the double slit, then we will have double slit diffraction pattern. So which means electrons are quantum particles. And the derivation of Vlasov was not assuming anything about quantum mechanics. And my question is, okay, so how they are related? So how? So I want to talk about now about from this question. I want to talk about fermionic manybody Schrödinger system. So in classical mechanics, maybe everybody's doing this. So classical mechanics is describing a particle system. There are two big branches. One is about particles, Newtonian mechanics or Hamiltonian mechanics, equivalent. So in Hamiltonian mechanics, they are considering total energy of the system, particle system. And then the total energy is sum of kinetic energy and potential energy. And so P squared over 2m plus that kinetic energy plus potential energy. Okay, good. And there is another branch which is about wave mechanics. And waves, thanks to Fourier, we know that any wave can be any wave in physics sense that can be decomposed into plane waves, sum of plane waves, weighty sum. And total energy of wave, if we want to make it align, total energy of the wave is a weighty sum over W, omegas. Okay? And then so this is giving us the total energy of any wave. And to obtain the same function, same thing, we can just derive with respect to time. Actually. Here one can see. Here one can see by derivating this with respect to time, this omega will come here, and we will have weighty sum. So time derivative is giving us a total energy of a wave, and momentum. Okay, again, it's a weighty sum over k, and then in that case we derive with respect to spatial variable. Then momentum can be attained by derivating with respect to spatial variable, and as here written, momentum energy, kinetic energy is a square of momentum, so which means we apply momentum operator twice, which we have minus Laplace. Okay, and from the previous picture, we know that we observed that electrons are following, having some nature diffracting, so it should be considered as a wave. And then if we apply this analogy to this wave analogy to here, we obtain Schrödinger's equation, which is exactly how Schrödinger described in his paper. Okay. Like this. the Schrödinger said, okay, total energy of the system should be right. The left-hand side is about total energy, and the left-hand side is about the summation of our kinetic energy plus potential energy. And this is nothing but Schrödinger's equation. And this is somehow easy because this is linear equation. V is nothing to do with the psi, and one can solve it by at least formally by having this. We plug this and that to the equation. Okay. This is what Schrödinger said. Okay, cool. So one particle with the external potential, you know everything. But as I said, electron, like the plasma consists of a lot of electrons, many. So we want to talk about many-body quantum mechanics. So here we have wave function, which was an object describing electron, and now we have n variables to describe n electrons. And here we have kinetic energy for each electrons. We sum them for the total energy. And here we introduce the interaction energy between two particles, because before maybe there was one particle, so there was nothing to interact, and now ice particle can talk to base particle, so we want to include that interaction. So here this is the interaction between particles, and I omitted external potential. Okay. So this is many-body quantum. Yeah, and we want to solve the Schrödinger's equation with this operator instead of H equal. Good. So I want to talk about now the fermionic linear regime. So before there was no fermion or boson. Now I want to talk about fermions. And there is a parameter lambda to tune to have proper or meaningful limit. Okay, so we have to choose lambda. It depends, like regarding, remembering that we are considering fermions. So for fermions, it is known that the kinetic energy ground state of the kinetic energy of a ground state for three fermions, which are not interacting, is of order n to the 5/3 because of Pauli exclusion principle, which I cannot, maybe to save time, I don't talk about that, but yeah, so if you believe it, so if there are n particles, so the minimum energy that fermionic system can obtain is n to the 5/3. So which means the first term is over order n to the 5/3. Okay, and to have a meaningful limit, as n by taking n to the infinity limit, we hope that this is the same order. Otherwise, one will dominate, and we don't see the other, right? In the large n limit. So let's calculate what is the order of the second term. So we have n squared terms, right? More or less. And so we have lambda n to the square for the second. Then to have a right or meaningful limit, which is not really easy, or I would say some meaningful limit, we have to choose. We are forced to choose lambda to be n to the negative 1/3, so that everything is over order n to the 5/3. So now we write our Hamiltonian to be this, and we call this to be fermionic mean-field Hamiltonian, which means they are hooked to everybody, and somehow the mean here should be 1/n, but because of some reason that I described above, this should be the meaningful region. And I want to, and then I want to talk about dynamics, right? I want to talk about proper time scale. Here, as I told you, kinetic energy is about order n to the 5/3, which means that because we have n particles, typical velocity of one particle is about n to the 1/3. Velocity here is quite fast because we are taking n to the infinity limits, which means, okay, if we wait 1 second, like time of order 1, particle here is far away, so we don't see much, which means we have to use, I don't know, like very good camera to capture motion slowly. We need a slow motion camera, which means we want to scale time, we want to rescale time by n to the negative 1/3. So we want to see the physical phenomena where the typical particle is moving about over one length, right? So that's the proper time scale. So by rescaling time, we have, because there was a derivative, time derivative for the Schrödinger's equation, so now we have that one, n to the 1/3. And here we have mean field in the corner. Okay. Then now to make physicists happy, or yeah, to make coincide with physicist notation, we divide both sides by n to the 1/3, 2/3. Then now here we have just one n to the negative 1/3, and then we just rewrite to the h bar. And here, because there was nothing, so we have n to the negative 2/3, and we can call it h bar squared. And now we have 1/n. So this looks really mean field. Okay, so mean field here means that we are taking average. So this is called fermionic mean field Schrödinger's equation and body. And we want to see the dynamics of this. And yeah.
Let's see that this is going to be effective. Because you forgot the mass of the body.
Yeah, but like, yeah,
So,
you're,
the two species is the simply variables.
very good, very good. So I choose m to be 1.
Yeah,
Yeah,
I know,
yeah.
I know, but
And then they are not happy because h bar should be a constant. But one of my open-minded physicist friend told me, maybe this makes sense because, okay, any physics experiment is measuring, which is measuring h bar, maybe it's related to calculating the electrons, which is observable. And actually, according to, not Wikipedia, according to Google search that I found, was in the observable universe, the number of the electrons are not really, and then we plug that number to here, then which is not really far from h bar in log scale. So yeah, that's my advocation, but yeah, not my open-minded physicist friends. So yeah, so I want to talk about this, and people are talking about this system, and this is believed to be describing. Believe that this is describing many-body electron system, n-body electron system. Okay, so our system, we have two systems. One is Vlasov system, derived by Vlasov, using phase space, like continuum physics. But we know that actually that plasma is consist of a lot of electrons, and which should somehow follow n-particle Schrödinger's equation. Right? So how do we relate them? Right? So, connection. Okay, there are many words along this direction. So here, so n-body Schrödinger's equation, fermionic Schrödinger's equation we know, and Vlasov equation we know, and we want to obtain in some sense somehow as an object of the limit, right? By taking h, we fix h bar to the n to the negative 1/3, and we take n to the infinity limits, and we should obtain Vlasov equation. There are a lot of programs. So first, because we denoted here, we denoted h bar already, and 1/n. So as a mathematician, we are having freedom to take n to the infinity limits while fixing h bar. We do that, and if we do that, somehow one typical object, one typical electron is following Attendees equation. If you are familiar with NLS, nonlinear Schrödinger's equation, which is almost like And then from Hartree-Fock equation, by taking h bar to the zero limit, one can obtain the Vlasov equation, which is, there are many works about the direction. And because this diagram should somehow commute, there are also many works, not many works, I couldn't find many. There are some works deriving n-body Newtonian system, which is the Newfield equation, by taking h bar to the zero limit while fixing n. And then from Newfield equation, by taking n to the infinity limit, there are also some programs to derive Vlasov equations. And I want to just list the many authors. So for the mean field limit, which is the first vertical direction, there are many works by Benedictor, Agat, Edish, Yaxi, Porta, Rademach, Safirio, Schlein, Yao, and they derived the Hartree-Fock equation from manybody Schrödinger's equation. And as one can guess, so for the first time, they assume a lot of assumptions, and as time goes on, they are relaxing a lot of assumptions. And Chiara Safirio, she proved that this derivation works for even for Coulomb potential, even singular than Coulomb potential. Like if the interaction between electrons are Coulomb, which is basically proven. And semi-classical limit from Hartree-Fock to Vlasov equation, also there are many works. And the most recent work by Chiara Safirio, here she proved that for XS, maybe I would say about 1/2, until 1/2, she proved that she derived Vlasov equation from Hartree-Fock equation. Okay, and then so these are old works for this direction. I'm not an expert in that direction, but Dion and Paul in 80s, Dobrysin around that time, they proved each of each for limited interacting potential. Not they cannot cover Coulomb. And then, okay, so as I told you, we had the freedom to choose h bar to be independent to n, but I was not happy because while we were introducing mean field, fermionic mean field Schrödinger's equation, we assumed already that h bar is n to the negative 1/3. So I wanted to take limit directly. And yeah, there are a lot of works like from 80s, Sponswell, Narmuth, they proved the convergence itself vertically and diagonally for limited potentials, nice potentials, I would say. And then Goul's, Paul, they extended the work to be, yeah, it's nicer. And me and Li Chen from Mannheim, and you, her former student, we developed a technique to attack this diagonal direction using Husimi measure. And Jackie Chong, Laurent Lapèche, and Chiara Safirio, they used Wigner measure, also I will talk about, to derive the Vlasov equation diagonally. Okay? And so far, none of us is having Coulomb potential for the interaction potential, but we are trying. Here V means me and yeah, Chiara, yeah, and the other, some of the others. Okay. And yeah. So how can we relate? So as I said, we use Husimi or Wigner measure, but it's weird, right? So Vlasov equation is a function from phase in one variable, which means like R6, like position, momentum, and time. And the Vlasov equation was about electron density, which is positive number, real number. And we know that n part of Schrödinger's equation is like n variable function, so R to the n. 3 here means dimension and time, and it obtains a complex value. And how can we subtract those functions and measure. Measure here means we have to prove that this psi is converging to m somehow. So we need some metric, but we cannot really subtract directly. So we need some transformation. So one of the candidates is Husimi measure, and I want to talk about what the Husimi measure is. So for n particle wave function, we can define one particle reduced density matrix by using this. So let's say psi is a n particle wave function, which is having n variables, and one particle reduced density means we want to see the typical one particle's property. So how do we do that? Then, me as a mathematician, I look up answer, which is one particle reduced density matrix. So here, how do we do? So there is a psi n particle wave function, and we multiply that by its conjugate, but we put first variable to be x here, and here we put first variable to be y, and we from second variable to the nth variable, we let them coincide, and we take integration. We put it partial trace, which means we're somehow ignoring the information from the second particle to n particle. We remove them. Then this is a function somehow of x and y, and we rescale it by n. This is convention. You don't have to, but maybe. Now we have a function, and then if we consider this as a kernel of a operator, integral operator, we call the operator which is having this kernel, it is called one particle reduced density, and then physicist knows that by taking some Laplacian or taking some operator, you can basically see the structure and property of the n particle system by just observing. We can see many physical properties by just observing this one particle reduced density. And this is well known. And still this is not enough, because this was in C, and this was in C, and this is two variable function, but in spatial variable. So this is in C, and yeah, this is not enough. Okay. How do we do? So we want to somehow dequantize. People are calling dequantize, so we want to make it classical. And how do we do that? So we do some sort of Fourier transformation. But here, okay, so quantum mechanics is about wave function. And wave function is having information only about the space, right? So in space, the probability to find a particle at x is this. Right? So this is known that this is a probability. So this information should be encoded in the classical object as an x. So we have x here as a position, and then because if there is a particle x, and then that particle, if that particle is a wave, the information is propagating from x by like this, right? So, and that phenomenon can be measured by this. And if the wave propagating from one position to the world, to the space, is having momentum p, we have to measure it, and we have to encode it into a momentum. So using that analogy or that intuition, Wigner defined this Wigner measure, and we will see why it works well, and then we will see one example, convincing example that this is a nice object. Okay, so this is a Wigner measure, and this is now proper classical object because we have x variable and moment, spatial variable and momentum variable. So this should be a candidate to consider, to relate n particle quantum mechanics and one particle Newtonian mechanics. Okay, so I want to let you see an example, and I want to convince you why Wigner function is a nice object to see. Okay, so if there was a double slit, after double slit, the wave function, right after the double slit, wave function of an electron should be like this, right? If there were slit, electrons were like free to pass, and then for the other walls, the electron couldn't pass, right? And then in 1D. And then if we transform this using Wigner function, Wigner transform, so the Wigner function of this is this, okay? This object. And actually, so in physics, people know that the diffraction pattern is a Fourier transform of this one, which is this. Okay? And Fourier transform means it is observing the momentum space in fluid. In optics, they learn this. And then, which means if we project this Wigner function into the momentum space, if we integrate out, project here to here, because of this negative part and this two positive parts, they are canceling exactly. And then, and then we see this pattern, which is interference pattern, exactly. So we somehow reconstruct the diffraction phenomenon from Wigner function, and then if we think about laser of each of them will be like will diffract, and they are, if they are particles, they will diffract a little bit, and then they will form two Gaussians in real space. And if we integrate over this along this line, which is projecting Wigner function to the X space, we see this bump, and they are canceling each other. So that we don't see the bump at the origin. So that we really see these two bumps, and this is describing the particles of the electrons. Okay? So this one particle Wigner function is really describing, including all the information, and which is classical, and it is a classical to consider. So which is a nice transformation. Okay, good. But the problem here I faced before I started the project was, okay, this makes sense, everything makes sense. But didn't I say that Vlasov equation was describing the density of the electrons, which will never attain negative part. Right? Density cannot be, but this easy example is an easily attaining negative part, and I didn't know it. So how to remove it? Again, you look up some physics literature. There was a Husimi, and he said, okay, it is Wigner measure is attaining negative part. So how to remove it? Convolve it. If the negative part is small enough, if we have nice convolution, we remove negative part. So he said, okay, using this Gaussian function in phase space, we can convolve it, we can modify it, then we don't see negative part in this. We can prove it. Good. And the good thing is now this Gaussian has a very small standard deviation, bar, so which doesn't really affect the physics. I want you to use this. So I decide to, our group, decide to use this object to prove things. So, and then also there are people who did statics like ground state for fermionic systems using Husimi measure, and it worked well. So we used Husimi measure. Meanwhile, Chiarasapirio and the others were most of them were using Wigner measure. And Wigner measure is also nice because the support size of the support that attaining negative part is somehow over the square root of h bar, which is converting to 0, so it's nice. It's still nice. So, I mean, both are having sometimes, which is like Husimi measure is nice to consider. Sometimes Wigner measure is nice to consider. Both
But your analysis, H bar is fixed.
my analysis
This
is
analysis, you don't move H bar is a fixed number. So you don't go to semi-classical limit or.
me, yes. I take H bar.
This analysis,
This analysis, H bar is entering negative.
because okay, you shift from Wigner to Husimi to remove the negative.
Yeah.
But then your dynamics will no longer be in Wigner, will be Husimi.
Yeah, my dynamics will be in Husimi. And then we can generalize that Husimi measure by convolving with different functions. Okay, I would say. So I wrote it in Fock space formalism, but one can think of it as a convolution with a different function when down. And I call it generalized Husimi measure. And this should have like proper, like the same standard deviation. And correctly supported, that's what I said, and then like here proper momentum. That's my generalized Husimi measure. So if you know the Fock space formalism, I was calculating how many particles in the system, quantum system, having this as a wave function. So I was measuring how many electrons, right? This is number operator, measuring how many electrons are there in this shape. Good. Which means, maybe as a remark, which means this MQP at any QP be bigger than 1 because of Pauli exclusion principle. You got it? Like, because there cannot be this 2 electrons having the same weight. Okay. So the result. Okay, so to remind you, we had n particle Schrödinger equation in this format, but yeah. Remember that h bar was n to the negative 1/3, and this notation was to this is up here, and lots of equation there, and then to compare them, my theorem with the others was okay. So we define Husimi measure at each time. So okay, so we have initial data. We have initial data, and in n particle Schrödinger's equation, and we evolve it, and we at time t. We transform it to the Husimi measure. Okay, stay there. So here, at the initial time, the other dynamics is we make Husimi transform. We have one electron density, right? And then we evolve it using Vlasov equation. Okay. Then now we want to compare this object and this object. Okay. So for nice potentials, for some technical issue, we could improve it for very like nice cyst potential, which is even potential. So with this assumption, we could have proven that the one particle Husimi measure along this direction weakly converges to the solution of Vlasov equation as n goes to infinity. It's kind of weak result. Okay. So this was the question. Thanks. Good question. So here, our theorem was written for the Slater determinant of initial data.
Claude or just
the
same?
Yeah, just like. The Chiara's video can cover mixture state, but only. Yeah. So how? So now I'm ready to release most of you. What do we do? So here, this is for. I mean, I was a student, doing this calculation but you are having a lot of time to really calculate. So how do we do? So there was a Husimi measure, and I wrote the integral Fock space formalism, right? We derive with respect to time. Okay. We do it, right? And after dinner, especially. It's nice. So this derivative will hit here. Also, this derivative will hit here. And if you remember, there was nothing related to time, so the creation annihilation is fine. Okay. And then if time hits, we multiply I minus II, and then we make it Schrödinger's equation, and we change this time derivative into Hamiltonian and calculate everything until it makes sense. Okay. And then after 2 days, you find it, okay, I cannot do it better. You think, so you have to consider. Okay. Then if we sit down and see, this one was in Vlasov equation. This one was in Vlasov equation. Good, very good. But this one was never appearing Vlasov equation. This is very complicated, and we don't know how to do it. Okay, and how do we do as a mathematician? We do add and subtract. We do add and subtract. I mean, we have to hope these disaster terms should not be there, or we hope that these are very small, or these are very close to the thing that we wanted to have. Right? So this is what we want to have. These are what we have. So we add and subtract. So we add the proper one. We add proper one. Where is it? So we added proper one. There's I think here. Here. We add and we subtract it, and we see it. Actually, before there was this one, and we compare this with this, and then we notice that they don't seem close enough. Okay, then we add and subtract another one. We add and subtract another one to relate them. And then there was another one which looked promising. So we said, okay, maybe it's small. And we tried to prove it small. That was the strategy. So our main strategy was to calculate brute force until it looks like a Vlasov equation, and when we are almost there, we added and subtracted the properly somehow. Maybe it's not yet optimized, but we find it. We couldn't find a better way to. Until here we have it, and we added and subtracted until it makes sense, and then until we could prove that each of which are small. That was the strategy. How do we prove these are small? But yeah, because we don't have enough time. And so here, this one is somehow kinetic energy of momentum of the typical particle that we were calculating, which was P, and it should move not too much, and here because we had H bar, it's fine somehow. And then RS, RM are there, but typically I wanted to just show you that it was not easy. So the RM was main purpose was to show that two particle reduced density matrix, which I didn't introduce, but for the people who know, could be factorized more or less. And then to do that, again, we added and subtracted like proper things to compare. And then after we had three terms, it was enough to show that each of those three were small. And those two were, we could borrow the result from Benedicter-Potential line, because they had trace norm and Hibbert-Schmidt norm convergence, but they didn't have this because we needed them because we didn't have proper like H bar or something small in front. So we wanted to have this to be small, not this to be small, something to be small. So this to be small, but somehow we couldn't manage to use Benedict-Schleien's result to attain to make it zero. We couldn't bound it by something small. So what we chose is okay, because Hilbert-Schmidt norm and trace norm were not enough. We wanted to take something in between. And here, this is some sort of trace norm. Okay, some sort of trace norm. In the kernel sense, it's like trace norm, but which is not really, but somehow it's a trace norm in one variable. And for the rest, we took Hilbert-Schmidt norm, which is L2 norm, right? So this was L1, L2 norm instead of real L1 norm or real L2 norm in two variables. Okay. So the interesting thing was we could have proven basically this one, because those one were from Benedict-Schleien. This was interesting because, so according to Benedict-Schleien, the Hilbert-Schmidt norm for Hilbert-Schmidt norm for Hilbert-Schmidt norm for these were bounded by square root of n, and trace norm for this was bounded by n to the 3/2, and we could have proven that this, which is not really in between but almost in between, is bounded above by exactly something in the middle. So I think we were happy, and it was enough to show that each terms are small. Here each terms means, again, so we added and subtracted. And then we had these 33 terms to bound. We did. So yeah, typically for one term, as an example, I will show you, and by using time, you could prove 33 terms to be small, of small order. So yeah, in the end, we could prove that everything is everybody's happy. Yes. Thank you very much for your attention.
No,